Okay, so good morning, everyone. Welcome for day 10, so the last and final day. So I hope you have heard some interesting talks about fundamentals of combustion processes, and we also started to talk about applications. And I will summarize or close today's session with the final presentation about combustion fundamentals of explosion protection. So as an application example, how we can use our knowledge about combustion process to evaluate safety hazards when we use combustibles. So there, one topic, of course, is the ignition by electrical discharges. Of course, we need electrical power everywhere. We need it also in chemical and petrochemical plants. So, of course, it's of great importance to avoid ignition by electrical discharges. We have several types of protections based on fundamental research. But of course, if you would consider details with all the different type of electrical discharges we have, there is some ongoing research here too. So I have presented you already this examination of non-thermal plasmas where we have no breakthrough, where we don't have a spark, but we have heat formation and especially production of radicals due to electron impact reactions. So even though there is no hot plasma here, ignition takes place. Another example is the so-called opening discharge. So for a classical spark, you always need strong voltage. You have to be above the Paschen limit of several hundred volts. But of course, when you have such a closed system which you open, so we have here two electrons in contact. So there is a current flowing through this system, and then we open it. So you see, when we open it, a spark is formed. So what is happening? The electrodes are in contact, so current is flowing, but then we are opening them, and so we separate them. And in the contact between the two electrons, we reach very high temperatures. So the metal starts to melt, starts to vaporize, and then finally we got a plasma here, consisting also metal atoms and so on. So it's a quite complex configuration. And here we can reach ignition with a voltage around 21 volts. So at very low voltages, we also can achieve ignition of combustible air mixtures. So these are totally different ignition processes, but we always talk about ignition by electrical discharges. And today I will focus on the hopefully now well-known minimum ignition energy. So here we talk about normally breakthrough discharges, so very short discharges with respect to time, so 50 to 100 nanoseconds maybe. And the energy is stored in a capacitor, and then for a given spark distance or gap length here, we will see a spark, and the minimum ignition energy finally depends on the shape of these electrodes, of the distance here, and of course of the mixture composition at given pressure and temperature. So for each combustible, we know that this has to be adjusted, and the main usage, we have discussed it yesterday already, is to classify combustibles in different explosion groups or gas groups. So here you see it again. So this is a typical discharge, 15 nanoseconds. Within this very short time, the electrical energy is deposited into our hot small plasma volume. So it's very fast process here. At that time, nearly everything had happened, and then we just see some fluctuations here. The electrode distance for the most hydrocarbons and hydrogen are in the range of 0.5 to 1.7 millimeters. So this has several reasons. So the smaller the gap here, the smaller is the breakthrough voltage. And if we look at 1/2 capacitance times U square, of course, the smaller the voltage, the smaller the energy is. So for hydrogen, this can be down to 0.5 millimeter. However, if this is too small, we have, of course, cooling effects here. So there is maybe enough energy, but the flame cannot leave this area because it's cooled from the electrons. So for gases where we need higher energy, we also have to increase the spark gap. So for propane, for example, we need 1.7 millimeters. So there's a rule of thumb. This is in the range of the quenching distance of the combustible we want to examine. So hydrogen has around 0.6 millimeter. So the gap distance here is with 0.5 millimeter in the range of the quenching distance. So in classical setup, we can see here, so we have an optical accessible vessel. We have windows here at all sides. And now we want to focus here on 3 representatives for the 3 different gas groups. To C, hydrogen, to B, acetylene, and to A, propane. And you see here 17 microjoule, 82 microjoule, 240 microjoule. These are the respective minimum ignition energy of these combustibles at these specific concentrations. So and when we look into the system here, you see here we have our electrodes. We have now used in top-down configuration. We can also rotate them by 90 degrees, so this has no influence on the ignition process, or no significant. So we can adjust here these electrodes so that we can optimize the spark gap. We can exchange, of course, the electrodes to test other materials or other shape of the electrodes. And so this is in classical result from literature. So first of all, okay, you have to vary the mixture composition. So you see that at lower, leaner and richer mixtures, you need more energy. Near the stoichiometric composition, we found somewhere the minimum ignition energy. But as I said to you yesterday, this represents a mixture and an energy where we found in 1 of 100 experiments in ignition. So of course there is a large influence of probability here, and therefore when you compare different literature, you can of course find some deviations here. There is no the absolute minimum energy value. It always of course comes with an error margin, but of course you can see here the main influences, and this we also have discussed already. So the ignition probability, here you have experiments where ignition has occurred. Here we have experiments where no ignition has occurred. So there is an overlap here, and from this we can calculate a probability function, which results then in an ignition probability here around 1%, which is corresponding to the experimental MIE value. So this is what we know the electricity stored in the capacitance. We have the spark which is forming. So this we have discussed already. The final question is for us always, so what is the real thermal energy? So when we want to compare it with a simple 1D configuration, numerical calculations using simple 1D calculations, normally we net all these losses. We just deposit energy to heat up our system. And of course then there is a deviation from the numerical and the experimental results, and this is of course due to the fact that we don't know this precisely, and this we have to examine. So we can use so-called optical emission spectroscopy. So we collect the light from our hot region and use a spectrograph and an image intensifier and a camera to get spectra like these here. And so we vary energy and distance, so we vary energy density here in the experiments and measure then the spectra we see here. So what do we see here? This is a second positive system of nitrogen. So and from the shape of these bands here and the intensity ratio of these different bands here, we can calculate both rotational and vibrational temperatures. So these are not the ambient temperatures we have. The species are just distributed in the energy levels which does not correspond to the ambient temperature. And this is related to the energy we deposit into the system. Of course, after some time, due to collisions, they will fall back to the energy distribution here, and the different levels will fall back to the ambient temperature distribution. But for a short time after excitation, we will see that they are at different energy levels here. And this we can use to analyze the different discharge energies. So here you see in classical view of such a discharge here for hydrogen, so 0.5 millimeter, so maybe 200 micrometer width of this emission we see here. Here we see just the maximum of the intensity, and here we then see the corresponding spectra. And here we have varied the energy. So here we have nearly 4 times, 3.5 times the energy of this experiment. And so from this we can analyze the different lines, bands here to get the corresponding temperatures. So, and we of course have a non-thermal plasma. That means the virtual temperatures of the vibrational and rotational states are not equal to the translational temperatures, that means to the ambient temperatures. And there are often also electron temperatures given in literature, so which may have here then energy levels corresponding to much higher temperatures. So we see here we can vary the distance, we can vary the energy. We see no big influence here. So the rotational temperatures are always around 600, or here 525 degree Kelvin, sorry. And the vibrational temperatures are at much higher levels, so 4000 Kelvin. That means, of course, we have a non-thermal plasma, and this is in agreement with literature. So what is the main influence of this part here? So a lot of energy is deposited here into the vibrationally excited nitrogen, and this is something like an energy storage. So this nitrogen then collides with other molecules, and then the energy is transferred to the other molecules, leading to higher translational velocities, leading to higher temperatures. So we just store the energy here, and finally we need it, of course, for our combustion process. So for Schlieren measurements, so here we have an LED as a light source. We use a pinhole here. We have a lens system here. We have the observation volume here. Then we have a pinhole here, and then here with the camera. That means if there are density gradients in the system, the light is deviated in special directions, and this is then deleted by our pinhole. So we see this change of way of light with brighter or darker regions in our Schlieren image. So how does it look like? So here we see a temporal series of such of one specific discharge in air. So we have a distance here of 1.7 millimeter and a quite high temperature corresponding to the minimum ignition energy of propane. So here at what is it, 31 nanoseconds after beginning of the discharge, we see here a hot region. So there the energy deposition takes place, and after 150 nanoseconds, so the discharge is now over. So the electrical energy is deposited into our system. We see here a hot kernel, and this broadens with time, mainly due to heat conduction. And we have to consider here we have heated up very short the system, so from ambient temperature to 3000 Kelvin. So we also have higher pressure here. And so after a given time, so maybe here, so you can see clearly it here, so this pressure expands to the outer atmosphere. So here the pressure then falls back to ambient pressure, and we have a pressure wave which moves with the sound velocity of the cold mixture into the unburned region. And this, of course, also has a small influence on the temperature field in the surrounding. So, and then after 50 milliseconds, you see here a deformation of this hot gas kernel. So again, there is no electrical plasma anymore. This is just hot gas we see. And you see here how this is changing. So then we have plasma-induced vortices. So the cold gas mixes with the hot gas. And this, of course, has also a strong influence on the combustion process. This is something which I will point out later more in detail. So what we can yield from such experiments, so we get the radius of this kernel here as a function of time. So you may see it here. Here there's a small growth, and after this formation of this pressure wave, it's slightly larger. And we can, of course, examine the propagation of this pressure wave. And so this can be seen here in the experiment. This is the kernel radius, and this is the position of the pressure wave. And what we see clearly here is the higher the initial energy, the larger the kernel is. So the initial volume gets larger when we increase energy. So then here the pressure wave leaves our hot gas system. So we see this enlargement due to this process. Again, here we have high pressure in the volume, which then expands to low pressure. And then here we see more or less a constant radius for up to 10 microseconds. So heat conduction is quite slow, of course. And so we see the same with the pressure wave. So here it leaves the hot region, and then it moves more or less with the sound velocity of the unburned mixture through the system. And again, we see an influence of energy here. So the initial radius, of course, depends on the initial radius here. So the higher the energy, the larger the initial radius for the pressure wave to start. And the interesting thing is, when we assume proper heat losses in the calculations, this will be explained later here. This is just a comparison of numerical calculations. So you see, we see the same effect in the numerical part. The higher the initial energy, the bigger the initial radius of the hot kernel, and the bigger the initial starting radius of the pressure wave. So this initial radius is then an important parameter for the simulation. Again, in the simulation, we deposit energy into a volume. The critical parameter is the energy density. And therefore, of course, the radius is very important here. So the volume is given by the length of the gap and the area of the cylinder, so PR square. This is then, of course, very influential. You see, the higher the energy is, the larger this initial radius is. So we start here around 120 micrometer, go up to 200 micrometers at this low energy. So here we are below 0.5 millijoule. And then when we compare more in detail our experiments with the numerical simulations, so here we have the experiment in black, and these are different numerical calculations where we assumed heat losses. So we just haven't reduced the deposited energy by a factor, assuming heat losses. That means eta equal 1, there are no heat losses, and here we have 80% heat losses. And so you can see here the best comparison for the flame kernel and for the shock wave, pressure wave. We yield with an astonishingly high assumption that 60% of the energy are not stored into the system. So only 40% are used for the ignition process. So, but that's only a small part of the real world. So when we look here into typical ignition events, you see the deposition of the hot energy into the system, and then this flame starts smoothly to have a typical spherical shape. So, of course, at that time, the ignition event is no longer of interest. Now the combustion just takes place. But here we can see, hopefully, a little different configuration. You may see that the flame starts earlier on the right side. Again, so you see then an initial vortex formation, and then the ignition starts more on the right side, and then it moves with different velocities on the left and the right side, initial velocities into the system. And so here we have an ignition probability of only 1%, of course. When we use the same energy, we see just nothing. Nothing occurs. So we deposit the energy, and then we have large kernel formation, large vortex formation. So the hot gas and the cold gas are mixing, and finally no ignition is visible. So this we can examine here. Now we have selected images of the video you have seen here. So the three cases. So we have a hot kernel here. So again, 160 microseconds already, so far after the end of the electrical discharge. So here we have a hot kernel which then interacts with the surrounding due to vortices, mixing with the cold atmosphere, and finally in this experiment no ignition occurs. But of course it can happen that there is a clear spherical flame propagation, but also this is visible, that the ignition has taken place here on the right side. So we do not have only to focus on the energy and the volume of the plasma. Here, of course, we have to consider subsequent fluid interaction of the surrounding with our hot gas kernel. We can see this even more clearly here with ethylene, so where we have 4 different energies used. So at this low energy, I think no, so the ignition. Okay, what is not visible here, of course, that if we use lower energy, the ignition starts later. So, okay, for the Schlieren evaluation, okay, first we have a background subtraction, so then we get such a clear image, and then we use a specific function to find the edge of these areas, so we get here clear boundaries between burnt and unburnt mixtures. And then in this area here between the red lines, we calculate the distance from the spark, from the initial spark center. So here we get information about the left and right radius, and this we can then plot for an examination. So what we see with ethylene, at high energies, we can repeat the experiment at different times, and we see nearly no difference. So ignition and flame propagation looks more or less identical. If we reduce the energy to 2.9 times the minimum ignition energy, it also looks quite good. But I already had a minimum ignition energy the ignition energy of 2 times the MIE. We can see there's not this classical heating up the initial volume and then subsequent flame propagation. So here with the green results, so we heat up the system and then it takes some time. And then what we see here, it's getting broader, so larger difference. So this has ignited earlier. So in the green case, the upper line, in that experiment, it has ignited earlier than in the lower experiment. And this becomes more clearly visible here for this blue part here. So 3 experiments, 2 have ignited quite early. And here in this case, it has taken a long time. And what is not shown, of course, are all the experiments where no ignition has taken place. So not only this energy deposition and the volume is of interest. Of course, here we have a long ignition delay time. The mixing with the cold gas in the surrounding is of interest. which then influences, of course, our ignition process. And so this is well known from literature, from colleagues like Derek Bradley. So here in this part, this is dominated by the gas dynamics. So we deposit all the energy in a very small volume, so it expands, the pressure wave leaves the system and so on. And then after a given time, here we have chemistry and diffusion. And of course, this is then the interesting part here, leading to the things we have discussed here. So in hydrogen, it looks different. So here we have 4 cases. We can see that it ignites earlier as the flame reaches the outer part later than here. So, but it is not the fact that it had ignited earlier here. It's just that we deposit more energy into the system and the hot kernel is larger. So this can be seen here. So the higher the energy, the larger is this part where the gas dynamics are of importance. And then we have always, with nearly no fluctuations, the flame propagation into the system. And the big difference here is hydrogen Lewis number smaller than 1. For the hydrocarbons we have seen it's larger than 1. That means hydrogen loves this curvature. So this I have explained already in one of the previous lectures. So this is for hydrogen a preferred situation, while propane and ethylene does not prefer the situation, so they have a higher tendency to go out when the curvature is too large. Here you see it for propane. Again, the high fluctuations. This is due to the fact that these small radiuses of the system, the chemistry is very important, and this is negatively affected by the curvature for propane and ethylene, and positively affected by for hydrogen. So then we can go a little bit more into detail. We have an OH lift setup here, a YAG laser and a dye laser to get light in the wavelength in the range of 283 nanometers to excite OH radicals. We have also a second laser here, which we use to trigger the spark. So why we need to do this? So the experimental setup is just slow, and so we charge our capacitor and then we slowly rise our voltage. And at a specific time we reach the breakthrough voltage and the electrical spark will occur. And due to the fact that this rise in voltage is quite slow, this has nearly no influence on the breakthrough discharge. Nevertheless, when we trigger on this event, we have a problem. This is we have a lot of delay between triggering and firing the laser, getting an image. So we have to trigger on an internal event. So the breakthrough appears at a given voltage, but it appears due to the fact that we have some startup electron in the system formed by UV radiation from the sun or whatever. And this, of course, is a quite arbitrary process. And with the second laser, we just produce some electrons. That's it. We do not influence the ignition process, but we produce some electrons, and then it starts at the specific time, and we can then trigger the rest of the system and know precisely at which time we have to look. So, and here you see these OH images, again for propane. So here 200 microseconds after the beginning of the discharge, so we only see here hot gas, so there is no discharge anymore. And so we see here at the beginning it starts in the center, so of course there is a temperature distribution here, so near the electrodes it's colder than in the center, and then this enlarges here, and here we also see already some kernels outside the system, but here no ignition takes place. So finally the heating up is again in the center of the system, and for later times we then can see, so now we go, I have explained it different, sorry. So here is the discharge, here we see of course the plasma, and then the temporal evolution goes in this way. So here we have hot gas in the center, and then here we have already the formation of hot pockets outside this this hot kernel. So here the flame starts to propagate into the system, and so here we see it then more in detail. Here no ignition has occurred, so the flame goes out, the initial flame, if there was a flame, and here we see how this flame then finally propagates into the system. And then we can extract these radial profiles at different time steps for different energies, of course. So we see that at a given time, so here we have the hot kernel here with the OH, and then of course the flame propagates to the left and to the right. So this we can then compare with numerical simulations. So of course we have a high fluctuation here in the experiment. So you see here we have 4 different experiments for one energy configuration. So you see a lot of fluctuations here, but in principle we see the same. So the higher the energy, so red to blue to green, the larger the intensity is and the broader the initial volume is. So the energy of course has an influence, and then finally we see that this initial difference is also visible in the difference of the flame positions at a given time. So here this is the spark region, and here we have already the flame region of the system. This we can then to compare use to compare numerical results here with the experimental results, and so we see that this part here is then dominated by the chemistry, so the flame propagation. So the slope of the different curves corresponds quite good. Of course we have some differences here because this is our area of interest here, which we then have to adjust. So come to an end. For low energies we know already a lot. So we know how the energy is coupled into the systems. We know the losses through at the electrodes. So I've shown you an efficiency around 60%. But what we know not yet in detail is the influence of these vortices here we have here. So we have performed only 1D calculations. So you need to perform at least 2D calculations here. So there's still some work in the future, but for low energy discharges, we know the important factors, so energy density, and so on. So this is quite well understood. So OES has shown us no useful trends here concerning the temperature. So at each energy density it looks more or less identical. But Schlieren and OHP-Liv helps us to get more information from the experiments and compare it with numerical results. So with this, normally I would end, but for this lecture I have extended this with maybe 15 more minutes. So as I said, we now know it for the main combustibles, how this ignition by an electrical discharge takes place and what are the important processes. So for energy from 17 microjoule to 400 microjoule, we think we understand the processes here, what is important. Now, of course, hydrocarbons are no longer of interest. So even though you can see here source of global energy is mainly from hydrocarbons, renewables energy in the whole world have only a small contribution to energy production. We of course have this effect of global warming. So here we see the influence of natural and human factors to the global warming. And I've said in one of the previous lectures, so we have had ice age and hot periods in the Earth before, but this is here the green line. So if we would focus only on the natural factors, we should still have nearly the same temperature like in 1900. So it's man-made what we see here, and this is of course due to the gases with global warming potential like carbon dioxide. So in Germany we are already at 50% where we can use electrical power from renewable energy sources, and for heat, so heat pumps mainly, already 20%, nearly 20% is achieved. And for battery electrical cars, so China is much better here, where they have numbers of 40 to 50%. We have around 7.5% for renewables used in mobility. So this of course is quite a big step away from fossil fuel, but of course there are two big problems: 7 to 100%, 20 to 100%, 50 to 100%, and the sector industry is missing here. So we still need much more energy, which cannot be produced in Germany alone. And the second big problem is, here you see the power production per day over 1 year in 2022. And you see, of course, here we have wind and solar only, large fluctuations. And that's a big problem. There are big differences between peak maximum, peak minimum in a short period. And I was really surprised after kindergarten. Another German word is used in English language. That's the so-called Dunkelflaute. Dunkelflaute means we don't have sun and we don't have wind. So somewhere here, for example, you see for a very long period there is no energy production from renewable sources. And so that means we cannot have an energy system based only on renewables. We have to find something to store the energy. So we have seen yesterday this storage with compressed air. That's one possibility, of course. So we can compare here different systems. So I'm surprised that your compressed air system is not here. Maybe you can afterwards explain me where we can find it. But here we have, for example, pump hydro. So there we can store large energy quantities for a quite long time. But also we have very short storage systems, so high power flywheels. So batteries are quite good, but of course the costs are also quite high, so we can use it maybe for smaller quantities of energy, but not for gigawatt. So finally, so I don't know why pump hydro is also in time not higher here, but so chemical storage means we can store large quantities of energy for a very long time. So, and this is a typical image we see. Okay, we have our electrical energy from renewable sources. With this, we then produce green hydrogen. We can either compress it or liquefy it for transportation. With a lot of disadvantages, energy losses, and so on. We can transform it to different energy carriers, so carbon capture, Sabatier process, so we can form methanol, formic acid, methane, or use the Fischer-Tropsch process to produce even larger hydrocarbons, synthetic fuels, and so on. Also with losses, of course. Then here we have LOHC, so organic hydrogen carriers to transport the hydrogen. We have metal hydrides, we have shortly discussed. This is a possible way. We can use iron, which is not on this list, so we can reduce iron with iron oxide with hydrogen, and then burn this iron in coal power plants to iron oxide, and then again have a circle here reducing, oxidizing this iron. But today I just want to focus on this part here, ammonia. Ammonia, of course, is well known. We can use the Haber-Bosch process. So nitrogen from the air plus hydrogen gives us ammonia. Ammonia can be transported easily, and storage is also no problem for ammonia, even though it's toxic. But then the question is here, the big question mark, age to release. So there's a lot of research necessary. So how to crack ammonia efficiently to get the hydrogen back into the system. And so this we also have already seen. So ammonia itself has a very low burning velocity. So the laminar burning velocity is 6.5 centimeters per second. We need a high ignition energy, and the concept here can be to blend ammonia, for example, with hydrogen. So you see here, when we add hydrogen, we start here at 6.5 centimeters per second and end at 2.3 meters per second. So there's a significantly increase, and we also have a decrease in ignition energy. So what I will show you now in the experiment, there was a question yesterday if you use only mass flow controllers. Here we use a mixing vessel which we evacuate and then fill with air, hydrogen and ammonia using the partial pressure method. And then from this mixing vessel we fill our explosion vessel with the wanted mixture. We have a very small vessel here, just 100 diameter, spherical. So we have a volume only of half a liter, which is normally sufficient for ignition observations, but I of course will show you some limitations later. We can perform pressure measurements, and the ignition source is again a capacitive discharge. And in the previous slides, it looks like that we can vary this energy with a large degree of freedom. This is not the fact. So here we have a bank of capacitors which we have to combine to reach specific energy levels. So we cannot yield every energy in the given energy range. We have only selected steps which we can use. So here we see the minimum ignition energy of ammonia for two different distances, 5 millimeter or electrodes, 5 millimeter, no, distances, 5 millimeter distance and 50 millimeter distance. No, this is an electron diameter, so larger electrons are here. And here we see the minimum ignition energy at around 21%, so that means an equivalence ratio of 0.9. For hydrogen, this is a little bit broader here. Minimum ignition energy is phi equal 0.7, but it's, as I've said, very broad, so we keep now phi constant for all further experiments, and we add hydrogen from 0 to 20% to the system. So here we have 5 millimeter electrodes and 50 millimeter distance, giving us the minimum ignition energy. For hydrogen, we have 2 millimeter electrodes and 0.5 millimeter distance. So of course, again, big difference. So here we just keep this fixed. So we have 5 millimeter electrodes and 4 millimeter distance. This will give us not the minimum ignition energy for each mixture. Mixture means a specific amount of hydrogen and ammonia, but we want to keep this constant to finally compare also our experimental and numerical results based on one constant factor. So again, this is not the distance leading to the final minimum ignition energy for each combustible mixture here. So how does it look like for the pressure? So again, from 0 to 20%, we add hydrogen, and 0 to 20% means of the combustible. So we replace ammonia with hydrogen, and we always have an equivalence ratio of 0.9. So 20% of the combustible is then hydrogen, and here we have then 100% of hydrogen, just for comparison. So you see, for the pure hydrogen event, very fast pressure rise, as we have seen already yesterday, then cooling of the system. So then if we compare this with this pure ammonia plot, so very slow pressure rise, very slow pressure rise. What I have to say here, these T equals 0 corresponds to a given pressure trigger value. Therefore, they are not triggered on the electrode. Otherwise, this blue curve would be somewhere here. So we have here T equals 0 is the time when we reach this specific pressure value. And if we add then hydrogen, you can see how the slope rises. So it's getting faster and faster when we add hydrogen to the system. So this we calculate. First of all, we get higher pressures when we add hydrogen, because the losses at the wall becomes less and less important, and the pressure rises faster, as shown before. When we look now at the ignition energy, so here we have a logarithmic scale. Here we have the experiments where we have seen no ignition in 1 of 10 experiments in black, and in red we have the energy where we have seen ignition in 1 of 10 experiments. So again the problem is we just have here fixed values in our capacitor bank. So there's of course always a step width, so this is not very precise. The error here is quite large. So, but nevertheless, you can see when we add hydrogen, we will see a decrease of energy necessary for ignition. And here we come to an end. We limit the system to 4 millimeter gap width. And with this, there is a minimum breakthrough voltage. And this is here a given energy level. So we cannot increase hydrogen anymore, or we can increase it, but we won't see any influence, because we always would use an energy of this level here. So, and we would always see an ignition. So to continue these experiments, we would have to reduce the electrode distance. So then what is the outcome here? So please remember the Schlieren images we have seen at the low energies. I will show this for hydrogen again. So we can see here the energy deposition into the system. We can see the hot kernel. We can see sometimes the plasma discharge. So the deposition time for one image is 33 microseconds. So if we are lucky, the spark is in this time and we can see it, but we cannot always see it. So here we see this bright region here at the beginning, and then already a very large vortex system at these high energies. So 114 millijoule. The old image I've shown, we were around 240 microjoule. So a factor of nearly 1,000 difference. So in this you can see here we have the different amount of hydrogen in the system, and here we have the corresponding minimum energy necessary for ignition. So we start at 0% hydrogen, pure ammonia air mixture. We need 114 millijoule, and we have a very large kernel here. So the plasma, of course, is quite strong. And here already at 20% of hydrogen, we need around 1.1 millijoule. And we nearly can't see the initial hot kernel. And if we would continue this down to pure hydrogen air mixture, we are in the range of 70 microjoule. Of course, then it's much smaller again. And then we can see the temporal development. So here in this first image, we always see the discharge, and this is also the reason for this numbers here. We have not t equals 0. Again, we have Schlieren image, so we have a deposition time of 33 microseconds. And the first image is always where we see the first discharge occurring. So it appears maybe at 10 equals 0, but the image started to be taken at 12.9 microseconds for 30 microseconds. So this is the reason for these odd numbers here. And then, okay, we see the formation of the hot kernel after end of the discharge. And you see already this is much bigger than here. So we increase hydrogen here, and we need to increase energy here. And when we continue then in time, so for these hydrogen dominated mixtures, we can see a nice flame ball with a smooth surface. So ignition has taken place here in the center quite early, and then the flame propagation dominates everything. Here for ammonia, it looks different. So here we have deposited much more energy, so we have a lot of vortices formed due to this plasma interaction. So we have mixing here, strong mixing field, of course, that influence the ignition. But of course, we can see it here for the different energies. But again, this looks totally different compared to the pure propane or hydrogen results we have seen before. We then again can extract the radius here for further analysis, for example. And here we see the radius as a function of time. So here for pure ammonia, we deposit a lot of energy into the system, so the initial radius is quite large. That's again the spark-dominated region. And already for 20% of hydrogen, this is much smaller. And then after it's given, then we reach a time where the chemistry dominates the system. So we see this flame propagation. This we get the derivative of this. So we see here a time which is dominated by the spark, and then we get a more or less constant propagation to the outer atmosphere, dominated by the flame velocity. This we cannot see for pure ammonia. Our window has only 5 millimeters here in diameter. So already the energy deposition brings us here to the end. But again, for the other gases, we can see clearly the difference between spark-dominated region and region dominated by the chemistry. So we can compare here these in detail. Also for here given mixture around 10% of hydrogen when we use different energies, so we see the same effect. The higher the initial energy, the larger the initial plasma kernel. This is again the spark-dominated region here, and then we reach the flame-dominated region. So for higher energies, I've shown you that, of course, we also have to consider more factors when we want to describe the ignition by an electrical discharge in detail. So we still need, of course, energy. We need to know the losses. But here you see the strong interaction with the flow field is a very dominant factor. And therefore, we can use our simple 1D calculations to get some information here, but finally we have to make the step towards at least 2D or even 3D simulations. So with this, I would like to end my today's lecture and my part of this lecture at all. So thank you very much. Thank you. Do you have any questions concerning today's lectures?
Can we say that flame radius is dependent on the minimum ignition energy, and the energy deposition rate irrespective of mixture strength.
So you mean the flame radius depends on ignition energy?
And energy deposition rate.
Yeah, energy deposition rate has less influence, at least for the short times we consider here. And so we have done also some research where we compared 50 nanosecond energy deposition time with 1 millisecond energy deposition time. And there is a specific time where you can see an influence of the deposition rate. But I think it's somewhere below 1 millisecond, it has no influence. How long you deposit the energy, it depends only then on the energy density. But then the flame radius, of course, depends on the energy you deposit, and of course of the mixture composition. So at the beginning we have the spark dominated region where the energy is the important part, and this also defines the point where we start with the combustion. And then we have the chemistry dominated part, so then we have the subsequent flame propagation.
And in hydrogen and ammonia mixture slide where we have seen 0 to 20% volume percentage of addition of hydrogen, there we had you have said the ignition advance ignition occurs earlier. So and somewhere we haven't seen the flame kernel when 20% volume of hydrogen is added to that.
Mm-hmm.
So that means what? It's the advance, the ignition is delayed or what?
No, so we see the flame kernel also with 20% of hydrogen.
Yes.
So we see it here. So this is here 20% of hydrogen, the blue line. So here we see the spark dominated region, and here we see then the flame.
Now in that selection image we have seen an animation you have just shown us.
The Schlieren image, you mean?
Yes.
Yeah. Okay.
9.
You mean this here?
Yes.
So we see clearly here a flame. It's a very smooth, very nice torial flame.
At 2 nanosecond at the beginning.
Here, this you mean?
Yes.
So this is -2 microseconds. Again,
okay.
We collect here the gate time is 33 microseconds for one image. So in this 33 microseconds, we see this spark here, or this hot region then.
Okay. That means here the ignition happened earlier.
That's difficult to say. So that's the disadvantage of Schlieren. We cannot separate between hot gas from this plasma and hot gas from combustion processes. We see only hot gas. So we would need eventually here OH lift, or maybe better NH2 lift, if possible, to see clearly where is the flame front. But when you look here, it seems, even though that this case ignited earlier. But again, this is difficult to say. Here we have much more energy deposited, so the gas dynamics from the plasma are dominant here, so it can also have ignited somewhere here, but it's not then the dominating effect for the propagation. So we have no information about ignition delay time. And from the numerical work we have done is, we can say it's difficult to say. There is no clear trend. So you see, we also drastically reduce the energy. So the final ignition delay time is, I think, not has not so much big difference between this pure ammonia and this pure um, 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 hydrogen. Now I have to correct me. So there is a difference, and of course there is a big difference in chemistry. But the question is, when does this start? So if we would compare a pure hydrogen with a pure ammonia flame, hydrogen ignites much earlier. If we have 10% hydrogen and ammonia, this is still igniting like in an ammonia flame. So, but maybe here at 20%, the chemistry of hydrogen also becomes dominant. So this we have not examined yet.
I have a question in continuation to that. So we are mixing ammonia, hydrogen in the pre-mix chamber. Okay. Then you are supplying it to the so-called, let us say, a combustor. So does the size and shape of the combustor matters here, or it is the concentration only that matters?
What was the final part? What does matter?
That size, volume, or shape of the combustor through where we are doing this combustion.
Yeah, we have optimized this cell. It's a quite small cell with quite small windows to examine the ignition of hydrocarbons and hydrogen, where we need quite low energies and where the combustion is quite fast. So then there is no influence on the walls on the initial process or on the pressure profile. But for slow ammonia, you have seen we reach much lower explosion pressures. So because ammonia ignites in the center, then it goes up, reaches first the top side of the vessel, and then the flame goes down left and right. So here, of course, we have strong losses due to cooling. So this vessel is perfect for examination of ignition of hydrocarbons and hydrogen, where we need low energies, but it already gets some limitations when we look at the ignition process of pure ammonia. So you see here on these initial hot gas kernel formation dominated by the spark already reaches the end of our optical window. So we don't see the subsequent flame propagation, and you are seeing from the pressure profile then the subsequent flame propagation is also influenced by the small vessel size. So this we have already a bigger vessel, so, and we want to use it, of course.
Okay. So my next question is general question. So we know that combustion takes place in the gaseous phase. So is there any, by chance, is it possible it to happen at a solid phase or in the liquid phase?
I think it's coal. Coal is happening in the solid phase. So it depends on the combustible. But there are combustibles where the combustion is also taking place in the solid phase. So for alumina and so on, most of them we have vaporization, and then the combustion takes place in the gas phase. But there is some work with solid, some research work with solid fuel, and there is also work with liquid fuel. But here I'm not the expert.
Yeah, but both of them are first converted to the solid phase. I think the combustible gases, then those gases are in.
You mean to the gas phase?
Yes.
Huh?
Yes.
Yeah, that's for most of the combustible. That's the important step. So if you have a droplet, it has to vaporize. If you have a solid, it has also be transferred to the gas phase, and then combustion takes place in the gas phase. But there are examples. I think it's coal. coal also burns in the solid phase.
Okay. Okay, my last question is a global question. So, from the thermodynamics, we are telling that the temperature of Earth is decreasing, means Earth is cooling. We are saying that Earth is cooling. Earth and the solar planet system is cooling down, and but inside the Earth, temperature is increasing due to global warming something. So, how these both are contradicting to each other, and how do you look into that?
How do we hear cooling? Can you please repeat?
Means from the analytics of your geophysicist and other thermodynamicists that the earth, the temperature of earth is being reduced year by year. Means earth as a planet is cooling as an overall.
So that means we should have an ice age in maybe 10,000 years. Yeah? Yeah, but this can be wrong direction. So you mean that maybe this green curve finally goes down. This is maybe, I think I've read something like this, but I'm not an expert here, of course. But this is natural factors only. The Earth maybe should become cooler. However, we deposit so much carbon dioxide into the atmosphere that this is not the dominant factor at the moment. So in Germany, we can wait until the Gulf Stream would collapse. Then it would become drastically cooler in Germany. So then we would have a new ice age in Germany, but the rest of the Earth has global warming. This can happen. So again, this is maybe the natural trend leading to colder temperatures, but this is not what is dominant here.
Okay, thank you.
Okay, thank you. I have only one question. My question is on fire control and combustion control. So while we are extincting a fire or eliminating a burning or combusting fire, we use different materials, like what we may use water to extinct or chemicals. So my question here is there any chemical reaction between the combustible fuel and the fire extinguisher, or is it by heat transfer the fire is eliminating?
Yeah, okay, so this we haven't discussed in this lecture. So there are fire extinguishers mainly based on brome, fluor, so these halon substances. And they not only cool this, the flame, is halon the correct word? So brome and so on, they catch us some radicals. There are some chemical reactions then leading to the success of these fire extinguishers. So this is of course not only cooling of the system, then water would be sufficient enough, but also some chemical processes. Okay, then let's close this session. Thank you very much.
So we have closed this session.